Imagine a place in space where gravity is so strong that nothing, not even light, can get away. That's a black hole. It's not a hole in the traditional sense, it's not empty space. Instead, it's a tremendous amount of matter crammed into an incredibly tiny area. Think of it like taking the entire Earth and squishing it down to the size of a sugar cube. The gravity of that sugar cube would be immense, pulling everything around it inward with an unstoppable force. These objects are the universe's ultimate heavyweights, bending the very fabric of space-time around them like a bowling ball on a trampoline. These cosmic monsters are some of the most mysterious and fascinating objects in the entire universe. For a long time, they were just theoretical concepts, mathematical curiosities predicted by Albert Einstein's theory. Einstein himself wasn't even sure if they could actually exist. But as our telescopes got better and our understanding of physics grew, we started finding evidence. We saw stars orbiting what looked like nothing. We detected gravitational waves, ripples in space-time, caused by two black holes colliding. Now, we know they are very real and they are scattered all across our galaxy and beyond. So what are they really? You can think of a black hole as a cosmic vacuum cleaner, but that's not entirely accurate. Black holes aren't born out of nothing. They are the final stage in the life of some of the most massive stars in the universe. Let's talk about stars. Stars are giant nuclear furnaces. They fuse lighter elements into heavier ones in their cores. This fusion releases a tremendous amount of energy. That energy pushes outward as pressure. Gravity pulls inward. A star is in a delicate balancing act between gravity wanting to crush it and the nuclear engine pushing it apart. This balance can last for millions of years or even billions of years. But it can't go on forever. Eventually, a massive star starts to run out of fuel, at least 20 times the mass of our sun. It has fused lighter elements all the way up to iron. Fusing iron consumes energy instead of releasing it. The outward push suddenly stops. The star's core, which held up the outer layers, suddenly has no support. In that moment, gravity wins. The explosion is a supernova, and if the core is massive enough, a black hole is born. So what happens if you decide to take a trip toward one of these cosmic behemoths? Let's say you're in a very sturdy spaceship approaching a black hole. From a great distance you wouldn't feel much. As I said before, you could orbit it just like any other celestial body. The danger zone is the event horizon. As you get closer, the gravitational pull gets stronger and stronger. The gravity is so intense that it starts to affect time itself. According to Einstein's theory of relativity, strong gravity slows down time. For an observer watching you from a safe distance, say your friend back on Earth, as you approach the event horizon, they would see your spaceship appear to slow down. To your friend, it would look like you were moving in slow motion, frozen in time right at the edge of the black hole. But for you, inside the spaceship, your experience would be completely different. Time would feel perfectly normal. Looking back out at the universe, however, you would see everything speed up. As you get closer, another effect becomes very noticeable. Gravitational lensing. The black hole's immense gravity bends the path of light from the stars and galaxies behind it. The view outside your window would become a bizarre, warped funhouse mirror of the cosmos, a threshold you are about to cross. Now let's talk about what happens as you cross the event horizon. For you, the person in the spaceship, there's no big wall or flashing sign. You might not even notice the exact moment you cross it. You just float right through. But once you're past that point, there is no turning back. No matter how powerful your rockets are, you can't escape. The gravitational pull of the black hole is not uniform. The part of your body that is closer to the black hole gets pulled much more strongly than the part that is farther away. Let's say you're falling in feet first. This difference in gravitational force is called a tidal force. It's the same kind of force that causes the tides on Earth. But here, it's taken to an unimaginable extreme. This force will start to stretch you out. This stretching process has a wonderfully descriptive, if terrifying name: spaghettification. Your body would be pulled and elongated like a piece of spaghetti. The tidal forces would become so strong that they would overcome the chemical bonds holding your body together. You would be stretched longer and thinner, atom by atom. First, your bones would snap, then your muscles and tissues would be torn apart. Eventually, you would be stretched into a long, thin stream of individual atoms, all flowing down toward the singularity. It is the final, violent end to your journey into the cosmic abyss. Let's break down those two key terms we've been using, the event horizon and the singularity. These are the two most important parts of a black hole's anatomy. The event horizon is not a physical surface. You can't stand on it or touch it. It's an imaginary boundary in space-time. Think of it as the point of no return. It's the line in the sand. Outside the event horizon, escape is still possible, if you have powerful enough rockets. But the moment you cross it, you are doomed. The escape velocity, the speed you need to get away, is greater than the speed of light. The size of the event horizon depends on the mass of the black hole. A black hole with the mass of our sun would have an event horizon with a radius of about 3 kilometers. A supermassive black hole has a radius of about 12 million kilometers. The bigger the black hole, the gentler the tidal forces are at the event horizon. Now what about the singularity? According to our current understanding based on Einstein's theory of general relativity, the singularity is the very heart of the black hole. It's the point where all the mass is crushed down to a point of zero volume and infinite density. It is a place where our laws of physics as we know them completely break down. The singularity is where the universe's biggest secrets are hiding. So, what do we actually know for sure about black holes? For a long time they were just theoretical. But over the last few decades, we've gathered a mountain of observational evidence. The first major piece of evidence came from observing stars. Astronomers noticed stars orbiting something invisible. By measuring the orbit and speed of these stars, they could calculate the mass of the object they were orbiting. This is how we found Sagittarius A, the supermassive black hole at the center of our own galaxy. Another breakthrough came with the detection of gravitational waves. In 2015, the LIGO experiment detected ripples in the fabric of space-time for the first time. These ripples were caused by two massive black holes spiraling into each other and merging. The signal perfectly matched the predictions of Einstein's theory of general relativity. It was direct, undeniable proof that black holes exist and that they can collide. Then, in 2019, we actually saw one. The Event Horizon Telescope, a global network of radio telescopes working together, captured the first ever direct image of a black hole's shadow. They pointed their combined power at the supermassive black hole in the center of the galaxy, M87. The image showed a dark central region, the shadow of the event horizon, surrounded by a bright ring of hot, glowing gas. It was a stunning confirmation of our theories and a landmark achievement in science. We had finally seen the unseeable. We also know that black holes come in different sizes, from stellar mass to supermassive ones at galaxy centers. For all that we know, there is still so much we don't know about black holes. They remain some of the biggest puzzles in cosmology. The biggest question of all is, what happens at the singularity? Does it really crush everything to an infinitely dense point? Or does our understanding of physics just fail us there? Some theories of quantum gravity suggest that the singularity might not be a point at all. Another major puzzle is the information paradox. According to quantum mechanics, information can never be destroyed. But what happens to the information of something that falls into a black hole? If the black hole eventually evaporates through Hawking radiation, does the information disappear forever? The late Stephen Hawking wrestled with this problem for decades. Information being stored on the event horizon black holes as portals to other universes. And what's on the other side of a black hole? Is it just a dead end, a cosmic trash compactor, or could it be something more exotic? Bridges connecting to another point in our universe, bridges connecting to another universe entirely. While this is a staple of science fiction, there's no evidence to support it right now. Finally, how did the supermassive black holes get so big so fast in the early universe? Let's lighten things up with some mind-bending facts about these cosmic enigmas. Did you know that if our sun were to magically turn into a black hole of the same mass, not much would change for us here on Earth? We wouldn't get sucked in. The Earth and the other planets would continue to orbit it just as they do now. We would, however, freeze to death, because the sun's light and heat would be gone. Black holes aren't always black. The region around a black hole can be one of the brightest places in the universe. As gas dust and stars are pulled toward a black hole, they form a swirling, superheated disk around it called an accretion disk. The friction and intense gravity in this disk heat the material to millions of degrees, causing it to glow brightly in X-rays. These bright objects are called quasars, and they can be so bright that they outshine their entire host galaxy. Here's a weird one. Black holes can spin. When a massive star collapses, it retains its angular momentum, so the resulting black hole spins. It actually drags the fabric of space-time around with it, an effect called frame dragging. And finally, Stephen Hawking predicted that they slowly evaporate over time through Hawking radiation, eventually disappearing in a final flash. So, why are we so obsessed with these dark, destructive objects? It's because black holes are more than just cosmic curiosities. They are fundamental to our understanding of the universe. They represent the ultimate limit of gravity, a place where our best theories are put to the ultimate test. Studying them forces us to confront the deep connections between space-time matter and energy. When we try to understand the singularity, we are pushing the boundaries of human knowledge, searching for a new theory of everything that can unite the world of the very big with the world of the very small. Black holes also play a crucial role in the life of the cosmos. Supermassive black holes at the centers of galaxies are not just passive residents. They are cosmic engines that shape their surroundings. The intense radiation and powerful jets that blast out from their accretion disks can regulate star formation within the galaxy. The study of black holes drives technological innovation. To see the unseeable, we have to build incredible new instruments. The LIGO detectors that herd gravitational waves are some of the most sensitive instruments ever built. The Event Horizon Telescope required connecting radio telescopes across the entire globe, creating a virtual telescope the size of the Earth. Pushing to answer these fundamental questions leads to new technologies with benefits far beyond astronomy. It's a testament to human curiosity and ingenuity, a drive to explore the unknown no matter how challenging. In the end, black holes remind us that the universe is a wild, strange, and wonderful place, full of mysteries still waiting to be solved. They are the keepers of cosmic secrets, and we will keep looking into the dark, listening for their whispers. If you found this journey into the abyss fascinating, don't forget to hit that like button, and for more cosmic content make sure you subscribe. Keep looking up.